Hey everyone, welcome to part 3 of my homework 1 submission for computational methods. Here we're going to explain and code a function that calculates a surface point distance r equals zero point 0.5 away from the central helix for an arbitrary angle theta between n and the cross product t cross n. Why is it necessary to use the cross product t cross n, right? So let me actually answer the second question first. So basically what we're trying to do here is we're trying when to with those surface points, right, that are r equals zero point 0.5 away from the curve, what we're going to be taking is this kind of wireframe curve and turn it into like a hose, right? So like a conical section or like a 3D sort of surface, right? That's the whole point of a surface point, right? And if you look at the TNB reference frame, right, so T cross N is nothing more than this binormal curve. And so why do we have to use T cross N, right? Well, I mean, if you think about it, what we're trying to do is turn this point and create it into the surface, right? So when you have when we're looking for our angle, we want it to be between one of the vectors to come out of the plane, because if the vector doesn't come out of the plane, we can't actually revolve, or we're not revolving anything, sorry. We actually can't make that surface, right? So if you notice, all other combinations of cross products lead to vectors that share a plane um, with our helical curve. But the binormal vector does not share the plane, which is why we have to use t cross n. And then now to actually do this, it's actually pretty simple, right? So we're going to define a function surface that takes in our t and our theta. Um, let's just, um, right, so our t and the theta, right? And then so our tangent is going to equal how do I say? Just going to equal tang at t, and then normal is going to equal norm at t, right? And then, as easy as you can think, the binormal equals the cross product, right? J and p dot cross, the tangent, and the normal. Very, very easy, right? And then, so what we're actually doing here, right, is if you think about when you parameterize a curve, right? So you have x and y, and to put that into polar coordinates, you do x equals r cosine theta, y equals r cosine theta, or y equals r sine theta, right? But the way you actually do that is through matrix multiplication, right? So you take x and y and then the r cosine theta, r sine theta, and then you multiply those matrices together, and then eventually the way you actually get polar coordinates is through matrix multiplication. So we're going to do the same thing here, except our x and y are going to be the normal and the binormal, right? So if you think about this, first we have to make our x, y vector, right? So it's going to be, we're going to say return j and p dot stack, right? And then we're going to stack the normal and binormal vectors. The normal and binormal vectors, and then we want to multiply it, right? We want to multiply it by our the curve that is parameterizing our surface point. So our surface point is 0.5 away, right? But it's still going to be circular in the sense that it's going to be r cosine theta, r sine theta. Just the r is going to be zero point 0.5 because it's like a circle of radius 0.5 away. If you imagine the curve of our surface points, right? And it's not going to be cosine t, it's going to be cosine theta. So our surface point is going to be an array, right? And it's going to be zero point 0.5 times j and p cosine of theta and zero point 0.5 times j and p sine of theta, right? And then at surface point. So this just means we're multiplying the matrices together. So now if I print surf 0, 0, Um, 0, 0. Give me a second and let me figure out why this isn't actually printing. All right, so I think I realized why. I realized I just called tang and not tangent. Wait, no, this is right. Sorry, it's not here that I should change it up. It should be here. I realized I called tangent and normal, and now it's still not working. Um, Sorry, give me one more. All right, I realized what was up. So basically, I had this right. I had this in the indent, and so I guess it thought it was part of the function, right? So if I take this out, it's negative 0.5, 0, and 0, right? And if you think about that, I said t was 0, I said theta was 0. So basically, it's at the starting point, right? And if theta is 0, this resides on the xy plane. So basically, it's just saying it's negative zero point 0.5 away, right? And that makes sense because we said r is 0.5 away from the surface, right? But what we want to return is the actual point, right? And so that actual point, so this is just a difference relative to our surface, but I want to return the actual point. So I'm going to take our surface at t and add it to the relative point, and now we get 2.5, 0, 0, right? And that makes more sense. So that's what the actual surface point is. And in the next part, I'll actually graph a combination of all of the surface points, and we'll see what the actual hose ends up looking like. Thank you guys for watching this video. Bye bye.